Hello one and all, welcome to another online video by Einstein Academy. In the last video, we looked at the content from Learning Outcome C from the topic of the gaseous state from the JCH2 chemistry syllabus. In this video, we are going to look at some past year A-level question that test on Learning Outcome C from this topic in the JCH2 chemistry syllabus. As a recap, Learning Outcome C, candidates should be able to state and use the general gas equation PV equals to nRT in calculations, including the determination of MR. November 2009, paper 1, question 7, use of the data booklet is relevant to this question. Which expression gives the pressure exerted by 1.6 times 10 to the power minus 3 moles of N2 in a container of volume 3 dm cubed at 273 degrees Celsius? Okay, so in order to solve this question, we of course need to make use of the general gas equation PV equals to nRT. And I remind all the students out there, the pressure must be in Pascal, the volume must be in meter cube, N is just the number of moles, R is the molar gas constant 8.31, which you can find in the data booklet, and temperature is in Kelvin. Okay, we can rearrange this equation because we would like to calculate the pressure. So nRT over V, N is given in the question to be 1.6 times 10 to the power minus 3, just the number of moles. The molar gas constant is 8.31. The temperature must be in Kelvin. So I remind you all again, the way to convert the temperature in degrees Celsius into Kelvin is to add 273 to it. So if we have 273 degrees Celsius, it will be equals to 273 plus 273 to it, so that we can convert it into Kelvin. And we need to do so because that's the units that has to be used in the temperature in the ideal gas equation. So this is 273 plus 273. And volume has to be in meter cube. So this is in dm cube. 1 dm is equals to 10 to the power minus 1 meter. So if we were to cube both sides, 1 dm cube would be equals to 10 to the power minus 3 meter cube. Okay, so this is the way to convert dm cube into meter cube. And if we have 3 dm cube, then of course it will just be 3 times 10 to the power minus 3 meter cube. And this will be the answer. If you were to compare this expression to all of that given in A, B, C, D, the answer will be D, because that's the one that matches. Okay, so that's the answer to this question. November 2010, paper 1, question 7, the value of PV is plotted against P for two gases, an ideal gas and a non-ideal gas, where P is the pressure and V is the volume of the gas. Okay, so if you were to recall the content from the previous lecture, right? It is not explicitly stated in this question that temperature is constant, but we do have to assume that that is true, because only if temperature is constant and N is constant and R is constant will PV be a constant, and only then will it be true that when you plot PV against P for an ideal gas, will you get a horizontal line. So I repeat again, although in this question it's not explicitly stated that temperature is constant, we have to assume that it is true because of the fact that PV against P, it's a constant for the ideal gas. However, for the non-ideal gas, it does not obey all the assumptions of the ideal gas assumptions. So it will actually dip down first and go up after that. If you're interested in the reasoning and you do not remember, again, you can refer to the content from the previous video. Okay, so which gas shows the greatest deviation from ideality? So as I've already mentioned, if a gas does not obey the assumptions of the ideal gas assumptions, then it's going to deviate away from the calculations by PV equals to nRT, and hence it will also show the greatest deviation from ideality. And the main assumption that is always not obeyed by real gases is always the fact that real gases actually contains significant intermolecular forces of attraction. And generally, the stronger the intermolecular forces of attraction, the greater the deviation from the assumptions on the ideal gas equation, and hence the greatest deviation from ideality. So our job here is to figure out which one of these four molecules actually has the strongest intermolecular forces of attraction. So for ammonia, the molecular formula is NH3, and hence it is actually that the intermolecular forces of attraction is actually that of hydrogen bonding. For ethene, it's actually this molecule. This is the molecular shape or structural formula of ethene. And because there's no polar bonds, it will be that of ID-ID interactions. For methane is CH4, again no polar bonds, so it's ID-ID interactions. For nitrogen is N2, hence it's also ID-ID interactions, and hence Among the 4 molecules, ammonia actually has the strongest intermolecular forces of attraction, causing it to deviate furthest away from ideality. And hence the answer to this question is option A. November 2011, paper 1 question 4, a given mass of ideal gas occupies a volume V and exerts a pressure P at 27 degrees Celsius, at which temperature will the same mass of the ideal gas occupy the same volume V and exert a pressure 2P. So we go back to the ideal gas equation, PV equals to nRT, but in this question, there's actually a given mass. So we have to re-express the number of moles as mass over mR. Okay, so I'm just going to write N as M over mR. And then because we are talking about the pressure, so again, I'm going to further rearrange it to bring the volume over to the other side. So this is M over mR multiplied by V multiplied by RT. Okay, we want a pressure of 2P, and then it's the same mass of the ideal gas, so we can put the expression M. The mR doesn't change because we're talking about the same gas, and it's the same volume, so we can put V here. And then, of course, R doesn't change because it's just a constant. Okay, sorry. And one thing that I would like to put in this expression here is that because it's 27 degrees Celsius, right? So we need to change it into Kelvin. If we change it into Kelvin, we will add 273 to this. So 27 degrees Celsius corresponds to 300 Kelvin. Okay, and hence the temperature here, right, is actually 300. Okay, so now, right, we would like the pressure here, when it's 300 Kelvin, it's a pressure of P. We would like a pressure of 2P, and hence, we actually need to double the temperature from here. So we need to double the temperature from 300 to 600 in order to achieve a pressure of 2P. And hence, the answer to this question is the temperature needs to be 600 Kelvin. November 2007, paper 2, question 1D, 1E, and 1F. At sea level, an inflated bicycle tire contains 670 cm3 of air at an internal pressure of 6 bar and a temperature of 20 degrees Celsius. The instructions on the side of the tire states that, safety note, maximum internal pressure is 8 bar. At sea level, atmospheric pressure is 101 kilopascal. The tire will burst if the difference between the internal pressure of the tire and the external pressure becomes too great. And they also tell you that 1 bar is 100 kilopascal. Use the general gas equation, PV equals to nRT, to calculate the amount in moles of air in the tire at sea level. So we go back to PV equals to nRT, and we would like to calculate the number of moles, which means that we want N is equals to PV over RT. Okay, and the pressure in the interior is 6 bar, so it will be 600 kilopascal, which is 600,000 Pascal. Okay, remember we have to put it in Pascal. The volume is 670 cm3. So 670 cube, in order to change it into meter cube, we need to multiply it by 10 to the power of minus 6. So for those of you who are not familiar with this unit conversion, right, 1 cm is 10 to the power of minus 2 meters. So again, we cube both sides. So 1 cm cube is 10 to the power of minus 6 meter cube. And of course, based on that, 670 cm cube is 670 times 10 to the power of minus 6 meter cube. R is 8.31, and then the temperature, it's 20 degrees Celsius. So we add 273 to it to change it into Kelvin. So 293. If I were to quickly punch this into the calculator, 600,000 multiplied by 670 times 10 to the power of minus 6 divided by 8.31 and also 293, we will get a value of 0.16510, which is equal to 0.165. So we would leave this to 5 sig fig as an intermediate working, and then the final answer should be given to 3 sig fig. The reason we leave it to 5 sig fig in the intermediate working is such that if we need to use the value, the number of moles in the later part of the calculation in the question, we will use the value that is to 5 sig fig so that we maintain the accuracy of the final answer in the later part of the calculation. The next part, bicycles may be carried in the luggage hold of an airliner, a part of the aircraft which is not always heated or maintained at a pressure of 101 kilopascal. Typical values for the conditions in the luggage hold of an airliner at a height of 10,000 meters is a temperature of 5 degrees Celsius and a pressure of 0.28 bars. A bicycle with the same tire inflated at sea level as described above is placed in the hole of the airliner. Assume that the volume does not change, of the tire does not change. Calculate the pressure inside the tire at a height of 10,000 meters. Include units in your answer. So of course, we go back to PV equals to nRT, and in this case, we want the pressure, right? So we would rearrange the equation to get this. The number of moles is as is previously calculated because the amount of gas inside the tire does not change when you change the temperature and the pressure. Okay, so the number of moles is 0.1651. Okay, so 0.16510. R is again 8.31. The temperature is 5 degrees Celsius, and we add 273 to it, so it's 278. And then the volume also does not change, and the volume will be 670 times 10 to the power of minus 6. When we do this, the answer will come out to be in Pascal. So let me quickly punch this again into the calculator. Times 278 divided by 670 times 10 to the power of minus 6. Okay, so this will be 569,283 Pascal. Okay. Or we can also write this to be 569 kilopascal if we round it off to 3 sig fig. Some airlines insist that bicycle tires should be deflated before the flight. Some other airlines do not. Should the tire described above be deflated before the flight? Use the data above and your answer to part B to justify your reasoning. Okay, so if you go back to the previous part of the question, right, it basically says that the tire will burst if the difference between the internal pressure and the external pressure becomes too great. Okay, and they tell you that if the maximum internal pressure is 8 bar, right? So if it's 8 bar, it will mean that it's 800 kilopascal, and the atmospheric pressure is actually 101 kilopascal. So the difference between the maximum internal pressure and the atmospheric pressure is 800 minus 101 kilopascal. This is the maximum allowed difference between the internal pressure and the exterior pressure. And if you were to calculate this, right, so 800 minus 101, 699. Okay, so basically the maximum allowed difference between the internal pressure and the exterior pressure is 699 kilopascal. So we just have to go back to the bicycle case and see whether the difference between the internal pressure of the bicycle and the exterior pressure, is it smaller than 699 kilopascal? Okay, so the exterior pressure inside the airliner is 0.28 bars, which is equals to, I'm supposed to multiply by 100 here to change it into kilopascal. So 0.28 multiplied by 100 is 28 kilopascal. Okay, yeah, so as in the pressure difference, right, between the internal pressure of the bicycle and the airliner is actually 569 kilopascal minus 28 kilopascal, which is equals to 541 kilopascal, right? And you can see that this pressure difference between the internal pressure of the bicycle and the exterior pressure is actually smaller than the maximum that is permitted. And hence it is actually safe for the bicycle, it's not required for the bicycle to be deflated, because it's the note actually, the conditions of the internal pressure of the bicycle and the exterior pressure in the airliner is actually lower than the maximum permitted. So the tire will not burst under these conditions, and hence it is not really justified that the tire described above has to be deflated before the flight. Okay, but I guess because many different tires have different constructions and it may burst under different maximum pressure differences, right? So maybe it is still justified that airlines will insist that they should be deflated in case that some bicycle tires, right, that does not have a higher standard that allows for a larger maximum difference between the pressures, those might burst in the airliner. Okay, so on to the next question, November 2008, paper 3, question 2D. When a mixture of the sodium salts of two different monocarboxylate acids is electrolyzed, a mixture of alkanes is produced. So it's given by this equation. So this question is tied in a bit to organic chemistry. So if you don't fully get it, it's fine. Okay, but we can just talk about this part, which is just based on the ideal gas equation. Electrolyzing a mixture of the sodium salts of the two monocarboxylate acids A and B will produce 3 alkanes C, D, and E, which could be separated by fractional distillation. A gaseous sample of 0.2 grams of C took up a volume of 87 cm3 at a temperature of 380 Kelvin and a pressure of 1.01 times 10 to the power of 5 Pascal. Use this data to calculate the MR of C and hence suggest its molecular formula. Okay, so go back to PV equals to nRT. Again, we have mass here, so we would like to change the N to be mass over MR. Okay, and then of course we get, and the goal of this question is to calculate the MR. So again, I can rearrange the equation to get M times R times T over PV. Okay, the mass is given to be 0.2 grams. Okay, it's in grams here because like when we express number of moles as mass over MR, the mass will be in grams. Okay, so this is 0.2 multiplied by 8.31. The temperature is 380 kelvins. The pressure is 1.01 times 10 to the power of 5 Pascal. And then the volume, it's 87 cm cubed, so 87 times 10 to the power of minus 6 meter cubed. Again, allow me to punch this into the calculator. So 0.2 times 8.31 times 380 divided by 1.01 times 10 to the power of 5. And then multiplied by 87 times 10 to the power of minus 6. Okay, so the MR will be approximately 71, I'm just going to round off to 72, okay? So suggest the molecular formula of the alkane, right? So alkane have a general formula of CnH2n plus 2. The MR of this, right, will generally be 12 times n plus 2n plus 2. Okay, 12 is because the AR of carbon is 12, so, and there's n numbers of the carbon, so it's 12n. This 2n is because the AR of hydrogen is 1, so that will be 2n, and then it will be plus 2 here, because this is the 2 extra hydrogens. Okay, if we set this to be equals to 72, right, then 14n will be equals to 70, and n will be equals to 5. Okay, so basically the molecular formula of the alkane will be C5H12. Okay, again, if you're not familiar with this because you haven't done organic chemistry, alkanes, just don't worry too much about it, but just stick to the understanding of this part of how we can calculate the MR given the information of this alkane C. On to the next question, November 2012, paper 3, question 1B, part 4. The following equilibrium exists in a sample of aluminium chloride vapor. So the aluminium chloride vapor is this, and when you heat it up, right, it will actually break up into the AlCl3, the monomer. Okay, when 1.5 grams of aluminium chloride was introduced into an evacuated flask of 250 cm3 capacity and heated to 500 Kelvin, the pressure inside the flask rose to 1.16 times 10 to the power minus 5 Pascal. Assuming the gaseous mixture behaves ideally, use the general gas equation to calculate the average MR of the mixture. So we go back to PV equals to nRT and we want to calculate the MR. So we will express the N again by M over MR. Okay, so PV equals to this, and we want to calculate the MR, right? So we will re-express the equation as this MRT over PV. Okay, for this case, right, when you put 1.5 grams of aluminum chloride, it doesn't matter whether it dissociates or not, but the total mass in the whole system will still be 1.5 grams. And hence, the mass will be 1.50 here. The R will be 8.31. The temperature is given to be 500 Kelvin. The pressure is 1.16 times 10 to the power of 5. And then the temperature, the volume is 250 times 10 to the power of minus 6. Okay, and then if you would punch this into the calculator, you will be able to get the MR, average MR of the whole system. The average MR is basically like, what is the percentage of this? The percentage of this multiplied by the MR of this plus the percentage of this multiplied by the MR of this. That's the meaning of the average MR. Okay, so for this question, I'm just not going to punch this into the calculator. I'm sure the students out there can do this on your own, and you'll be able to calculate the average MR of this given this expression. It's just a simple punching in for calculators and mathematics. Okay, so I'm just going to leave this question as this. Okay, so November 2015, paper 3, question 2E. The volume of 0.4 moles of hydrogen chloride gas was measured at a temperature of 300 Kelvin when various pressures were applied. The following results were obtained. Okay, so this is a table. At pressure 5 times 10 to the power of 5 Pascal, the volume is 1.924 dm cube. So if we were to multiply these two together, we will get this value. Okay, and they did it for another pressure. This is the resultant volume. They did it at this pressure, and this is the resultant volume. State how the value of PV should change with pressure for an ideal gas at constant temperature. So if it's PV equals to nRT and the temperature is constant, the R is of course constant, and is for a fixed number of moles of gas, then nRT is a constant, and hence the PV will be equals to a constant. Okay, and if PV is a constant, PV will not change with pressure. Another way of saying it is PV is a constant as pressure changes, even when pressure changes. Calculate the volume of 0.4 moles of an ideal gas at a temperature of 300 Kelvin and a pressure of 112 times 10 to the power of 5 Pascal. So again, just go back to PV equals to nRT, right? Rearrange the equation to get volume, nRT over P. The N is 0.4 as given here, and then the R is 8.31. The temperature is 300, and the pressure is 12 times 10 to the power of 5. So let me punch this into the calculator because we need it for another part, a later part of the question. So 12 times 10 to the power of 5. Okay, so we are going to get a volume of 8.31 times 10 to the power of minus 4 meter cube. Okay, and yeah, okay. Okay, so let me just change the dm cube, right? Because like, okay, anyway, the reason is because we are going to use it for a later part of the question. So like 0.831 dm cube. Okay, so copy and complete the third column of the table and use your values of PV to estimate the value of PV when P is equals to 12 times 10 to the power of 5 Pascal. Okay, so like this is just a simple multiplication thing. We are supposed to complete this table, right? So we're just supposed to take this, multiply by this. A very, very boring exercise. So I'm just going to do it to complete the question. So let me see. So this is 9.26 times 10 to the power of 5. Let me see, is that correct? Sorry, just give me a sec. Oh, sorry, this is 10 to the power of 6. Okay, and the other one is 15 times 10 to the power of 5 multiplied by 0.592. And this will be, sorry. This will be 8.88 times 10 to the power of 5. Wait, does this make sense? Okay, wait, sorry, let me just double check. Yeah, that's correct. Did I do something wrong here? That's 0.926. Oh, I'm sorry. 1, 2, 3. Sorry. This is 9.26 times 10 to the power of 5. Okay, must have punched something wrongly there. Okay, so we completed the table, and then we are supposed to use the estimated value of PV to calculate the use your values of PV to estimate the value of PV when P is equal to 12 times 10 to the power of 5. Okay, so like 12 times 10 to the power of 5 is like somewhere here, right? And you can see that when you double the pressure, you can see that this one, right, actually drops by 0.38 times 10 to the power of 5. And then like when you change, when you go from this to this, right, it decreases by a further 0. Let me see, 0. Yeah, it's also a decrease of 0.38 times 10 to the power of 5. So basically what it means that when you double the pressure, the product PV will decrease by 0.38 times 10 to the power of 5. Okay, so the thing is that when you increase from here to here, right, you will increase by an amount which is 0.38 divided by 5 times 2, right? Because like you only increase by, when you go from 10 to 12 instead of 10 to 15, it's only an increase of 40% if we treat this as the 100% mark, right? So we will increase by 40% of 0.38, and hence it will increase by 0.152 times 10 to the power of 5. So we'll take 9.26 minus that. And we will get a value. Okay, so if this is going to be 12 times 10 to the power of 5, the product PV is going to be estimated by 9.108 times 10 to the power of 5. Okay, again, okay, let me clarify one more time. When we double the pressure from 5 to 10, we would decrease the product PV by 0.38 times 10 to the power of 5. When we go from 10 to 12 instead of 10 to 15, right, we are only increasing by 2 units and not 5 units, right? So the amount that the amount that PV will change by will be changed by 2 over 5 times. Okay, so like 2 over 5 times 0.38 times 10 to the power of 5, right? This is equals to 2 over 5 times 0.38 times 10 to the power of 5. This is 0.152 times 10 to the power of 5. Okay, and hence, right, when you go from, you take this value, subtract 0.152 times 10 to the power of 5, and you end up with this answer. Okay, so this is the answer of the estimation of the value of PV when P is equals to 12 times 10 to the power of 5 Pascal. The next part, use your estimated value of PV to calculate the value of V when P is equals to this, right? So if the estimated value is this, 9.108 times 10 to the power of 5, so we would, in order to find V, we will take, so PV is equals to 9.108 times 10 to the power of 5, right? So they want you to calculate the V when P is this, right? So what we'll do is we'll take 9.108 times 10 to the power of 5 over 12 times 10 to the power of 5, which is this pressure, and we will get a value of 0.759 dm cube. Okay, and you can see that it is not the same value as that you calculated using the ideal gas equation for an ideal gas. And hence, the last part of the question is to suggest an explanation for the difference in the values of V that you have obtained in part B, based on the ideal gas equation, and part C based on the experimental results, right? In terms of the properties of HCl molecules. So again, this is just a test of whether you understand what is the reason for the cause of the deviation of real gases as obtained from experimental results in here as compared to ideal gases based on the calculation. And I already told you many times, the reasoning is always because that real gases deviate away from the assumptions of the ideal gas equation, and hence the most significant deviation is always the fact that real gases contain significant intermolecular forces of attraction. While real gases, there is negligible intermolecular forces of attraction. So for HCl molecules, right, the HCl bond is polar, and the Cl will be delta minus, and the H will be delta plus. So the way that the intermolecular force of attraction is PD-PD interactions, and since HCl has significant intermolecular forces of attraction in the form of PD-PD interactions, the values that you calculated based on the ideal gas equation will deviate away from these experimental results because the HCl is a real gas with significant PD-PD interactions between the molecules. Okay, so that's the answer for that part of the question. If you are confused over this part of the question, do drop me a message in the comment section. I'll read it and get back to you on whatever part that was confusing in this explanation. Okay, so the final question. Calculate the volume occupied by 5 grams of water at 25 degrees Celsius under a pressure of 4,000 Pascal. So this has mass, right? So we're going to use the ideal gas equation, but the one with mass. So again, change the number of moles into mass over mR. Okay, and we're supposed to calculate the volume. So let's rearrange this equation. mRT over mR times P. Okay, so the mass is 5 grams. The molar gas constant is 8.31. The temperature is 25 plus 273, so 298. The mR of water is 18. Okay, because water is H2O, right? So 2 plus 16. Okay, so that's 18. And then the pressure is 4,000. Okay, sorry, just let me write it out here. So let me again punch this into the calculator. So 5 times 8.31 times 298. And then we will divide it by 18 times 4,000. Okay, so this will be 0.17197 meter cube. Okay, if the pressure is raised to 4,500 Pascal at constant temperature, calculate the new volume. Okay, so if we go back to the ideal gas equation, PV equals to nRT, right? They say that the temperature is constant, the R is of course constant, and the number of moles doesn't change, right? Which means that PV is a constant. Okay, if PV is a constant and we know the pressure in the first, so if the PV is constant, we can do this because the product of the pressure and the volume cannot change, right? In the first section, the product of PV is 4,000 multiply, I'm sorry, this is actually 1, okay, because it's the pressure and the volume in the first instance. So 4,000 multiplied by 0.17197 must be equals to the new pressure multiplied by the new volume. And basically, if we take this multiplied by this divided by this, we'll be able to calculate the new volume. So if I again would punch this into the calculator, right, we will get V2, the new volume, to be equals to 0.15286 meter cube. Of course, we should round it off to 3 sig fig. Okay, so it will be 0.153 meter cube. Okay, so basically in this question, I want to exhibit how we can make use of this kind of relationships to solve questions as I've described in my lecture. Okay, like basically group all the things that's constant together, and then we can write the relationships between the things that are constant, and we can use that to solve for a new set of conditions. Like for example, in this case, right, the initial set of conditions is like 4,000 Pascal in this volume. If we were to change the pressure only under the conditions of constant temperature, then using this relationship, I can solve for the new volume in the new situation. Okay, so hopefully with this lecture, you now know how to apply what we have learned from the previous lecture to solving questions that addresses this learning outcome, state and use the general gas equation PV equals to nRT in calculations, including the determination of MR, which we have seen in a wide variety of questions in this video. So that will end off this video. And if you have any questions, just drop it in the comment section. If not, I will see you for another video where we will look at the last learning outcome from the ideal gas, from the gaseous state, from the JCH2 chemistry syllabus. As always, if you like this video, please hit and like the subscribe button. And I look forward to seeing you for the next video from the gaseous state. So thank you and see you again.